Good day. Pardon me. Happy Monday. How are you guys? Any questions at this moment? All right. Well, we have begun talking about work and energy. We started chapter 5. To briefly review, energy is this mysterious, invisible thing that matter can possess that allows matter to do stuff. And we talked about how work can transfer energy between various objects and also transform energy into different states. We talked about a few of those states, thermal energy, chemical potential energy, things like that. But now we need to look at some specific types that we're going to be using commonly in this class. So today, again, examining specific forms of energy that we will be using very frequently. The first of those forms is arguably the easiest one for humans to directly notice, the easiest form of mechanical energy for humans to directly notice, and that is kinetic energy, which is definitely one you guys referenced when we were working on Friday. Kinetic energy is the energy of motion. If you see matter moving, it has kinetic energy. Something had to do work to give it energy to get it moving. Formula for kinetic energy is Ke, that's as much as it gets abbreviated. Ke equals 1/2 times mass times velocity squared. So, to have kinetic energy, you need to have matter, and it needs to be moving. If matter is moving, it has kinetic energy. If either of these is 0, you don't have kinetic energy. Which means if you're stationary, no kinetic energy. If you don't have mass, you don't have kinetic energy, no matter how fast you're moving. So light has no kinetic energy for that reason. It has other forms. Now, this type of energy is somewhat relative because velocity is relative. From our perspectives, none of us are moving, at least not very quickly. And so from our perspectives, none of us have kinetic energy. But again, we are moving through space very quickly. So velocity is relative, therefore kinetic energy is relative. But we're going to operate primarily from an Earth-based perspective in this class. I will point out, kinetic energy, as with all forms of energy, is a scalar. You do not have directions for kinetic energy. You only either have positive when you are gaining kinetic energy or negative if you are losing kinetic energy. It's just a magnitude, not a direction. I will also point out that the velocity term here is squared, meaning that velocity matters more to kinetic energy than mass does. If you double mass, you double kinetic energy. If you double velocity, you quadruple kinetic energy. And that means it takes exponentially more energy to go fast. You've probably noticed this when running. If you run across campus, you're going to be tired a lot quicker than if you just walk across campus, right? That is because literally it takes more energy to go fast. You have to do exponentially more work to give your body the kinetic energy to be going fast. As this relates to your human existence, again, running sucks, but also it takes more and more energy for your car to go fast. You have to burn more fuel to get to higher speeds. So the most fuel efficient thing you can do while driving is be at the lowest speed in the highest possible gear. The other thing I'll mention is, this is one reason why space travel is hard, because to get to Mars in any reasonable time frame, you have to be going really, really fast. And to go really, really fast, you need a lot of energy, you need a lot of rocket fuel, and this is one reason why we don't have faster than light travel. Questions so far? All right. So, very quick sample calculations. Here we have two different entities with mass moving at two different speeds. Which example has more kinetic energy in it? It is A. I will ask though, are we going to plug 5,000 into our formula? Now, every formula in this class wants kilograms. So how many kilograms is 5,000 grams? Very good. Oh, no, I was wrong. It's not the bowling ball. I got my examples mixed up, sorry. So 5 times 3 squared is going to give us 22.5 joules. And then human walking, 100 kilograms times 1 squared. I did say that the velocity matters more, but the masses here are so out of proportion that it overpowers it. Because here we get 50 joules. So depending on the mass of your body, walking is actually more taxing than chucking a bowling ball. So, sorry, I misspoke a second ago. Person has more kinetic energy in this scenario. I crossed my wires in relation to a different example. Questions thus far? Okay. While I've got these numbers up, I will point out, in order to walk at this speed, if this is your mass, your body would need this much kinetic energy in it at that very moment. But because of friction, you're going to keep losing this energy, and you're going to have to keep replenishing it by doing more work with your legs. So you have to keep doing work to maintain this level of energy. This is the constant requirement of walking, which is another reason why walking is more strenuous than throwing a bowling ball. Throw it once and you're done, but walking is constant. All right, so that's just one form of energy. There is lots of them, so let's now talk about a slightly weirder one. Gravitational potential energy. Now, I assume you're familiar with the notion of potential energy as a whole. The idea that energy can be stored for later use. Within our own bodies, we store a lot of chemical potential energy for us to use later. Batteries are also technically chemical potential energy because the energy is usually stored within a chemical reaction. But this energy is stored elsewhere. Gravitational potential energy is energy stored in an object's ability to fall. If you can fall any distance, there is energy stored in that fact. And that energy is released when you start falling. Because when you start falling, you do start gaining velocity, correct? You start moving towards the ground faster and faster. That means that some amount of energy that you possess must be transforming into the kinetic state as you descend. Because if you're gaining speed on the way down, you are gaining kinetic energy on your way down. And where that energy comes from is here. If you are in any sort of elevated position, there is energy stored in that fact that is released on the way down. How weird does that sound? Bless you. Bless you. All right. To describe this a slightly different way, let's look at the formula and then I'll explain what I mean, what the formula represents. GPE, which is just the best abbreviation I've got for gravitational potential energy. GPE equals the object's mass times the gravitational pull of the planet you're currently standing on times the height that you could be falling. Height above the ground, basically. I will point out, since energy is a scalar and doesn't care about direction, GPE doesn't actually care about that negative sign we usually put on G. So if it's not already on your formula sheet, please add an absolute value bracket so that you don't get a negative answer when you aren't supposed to. Energy does not care what direction gravity pulls, it just cares that it is pulling. And to give another perspective on what this represents, I am going to remind you of something different that we talked about on last time. Work. Look familiar, I hope, right? Work is force times displacement, and this formula tells us that whenever you exert a force on something and move it, you are using up energy, doing work, and giving that energy to whatever you are working on. That is true of pushing things along the floor, but it's also true of lifting things vertically upwards. Because to lift anything, you have to exert force. So right now I'm going to take this eraser of science, exert force on it, equal to or greater than its weight, and elevate it some distance. So this action is performing work. However much this thing weighs times the distance I lifted, I do that much work. And that means that I am giving this thing a certain amount of energy, right? So as it's just hovering there, it still has the energy that I gave it. And that energy is currently in this form. So GPE can not only be thought of as energy stored in an object's ability to fall, you can also think of it as the energy that was needed to get something up to a specific height, the work that was done to get it here, which can then again be released when it falls. To further prove my point, you can actually turn this formula into that one. When you lift something, the force you exert has to be greater than or equal to the weight of that object. And weight is m times g. And delta, displacement, if you're lifting something, is the change in height of the object. So I'll just write that here as delta H to make my point. We like to turn formulas into other formulas around here. So GPE is kind of weird conceptually, but I promise you've noticed it before, or at least you've interacted with it. When you lift anything, you are doing work to give that object GPE, and when that object falls, that GPE is released. All forms of potential energy are just waiting to be released and turned into something else. Most commonly, this form turns into kinetic energy when something starts dropping. And you know something has kinetic energy when it falls because it is moving. How do you guys feel so far? All right. Quick sample calcs. Which of these two objects has more GPE? It's A. Yeah. This is where I got my wires crossed a second ago. A, again, we're not ever going to plug in 5,000 grams. Instead, we're going to plug in 5 kilograms times the magnitude of 9.8. This is one of those formulas where we don't want that negative sign. So again, absolute value brackets. Height of 10 meters, and that should be about 490 joules. 100 kilograms times 9.8 times 10 centimeters, which is how many meters? Yep, 0.1. So that is only a grand total of 98 joules. Neither term is squared in this formula like it is in the kinetic energy formula, so one term does not necessarily overpower the other, they work together equally. Questions thus far? Okay. Now, there are way more types of energy than just those two, but those two are the most common ones we're going to reference in this particular class. They're both forms of mechanical energy. Mechanical just meaning physical, related to motion of matter that we can observe on the human sensory level. Since we now have two different forms of energy in our notebooks, we can talk about how they convert into and between each other. I hope you've heard before of the law of conservation of energy, which states that energy cannot be created nor destroyed. Energy simply will transfer between different states, and it will transfer between different objects. But the total amount of energy, both in the system and in the universe as a whole, will always remain constant. There's only a certain amount of energy out there, and we have to figure out how to use it responsibly. What this means for our math is, because we like to turn words into numbers around here, this statement translates directly into this equation. The total amount of energy something initially has will equal the total amount of energy something has after some sort of process has taken place. The totals on both sides remain the same, because again, the sigma means the total of the energy levels on either side. But on either side, those totals might be made up of different forms and different types of energy. But across the two sides, the totals remain constant. The total energy level is the same across all forms. And that means that there are several processes where, to use the two we have formulas for, where kinetic energy will transform into GPE over time and vice versa. And so I will now show you a few examples where that happens. Questions before that? All right. Let's start with an example that might look kind of familiar. We're going to launch a bowling ball straight upwards, which is not generally an advisable thing to do. 10-kilogram bowling ball is launched from the ground straight upwards at 4.5 meters per second. Suddenly realizing that bowling balls are just plastic coconuts. So, launching this thing straight upwards. We've done questions like this. Some of our first examples in this class involved using those first four formulas to track the motion of an object as it accelerates through the air. And those old methods do work for looking at this type of scenario. We could use our old formulas to figure out how high this thing rises to. But we're going to talk about this using energy first. We're going to talk about this using the new energy stuff. So my first question, what form of energy does this bowling ball have initially? If we consider the initial state to be upon launch. We start our stopwatch right as it's thrown. Kinetic. Initially, height of 0, velocity of 4.5 meters per second. Initially, this thing has kinetic energy as it's being launched from the ground. The process begins after it's been given kinetic energy, and every second after that, it will rise as some other process takes place. But to start with, it's going to have some amount of kinetic energy. I'm going to call that kinetic energy initial. How much of that form of energy will the ball initially have? We have everything we need to figure that out. To find that initial energy level, I'm going to use the initial velocity in our new formula. So 1/2 times our mass of 10 kilograms times our initial velocity of 4.5 squared. Make sure that that squared is only acting on the 4.5 in your calculators. And this thing should have about 101 joules of kinetic energy at the start of this process, right as it's been thrown or launched out of a cannon. So that is its initial energy level. Questions thus far? All right. Now, before I move on, actually, I want to point out that we can solve for this thing's initial gravitational potential energy, but if it's starting at the ground, what will its initial GPE be? 0. It doesn't have any yet. If it's starting at our lowest point, initial GPE would be 0. No matter how much mass this thing has. And so, in the beginning, all of its form is presently in the kinetic state. Now, my next question, what's going to happen to that kinetic energy as this object rises? It's going to decrease. Why will the kinetic energy level of the ball decrease on its way up? Gravity pulls it down. What does that mean as far as kinetic energy is concerned? The energy is going to turn into GPE, and we know this because the ball's velocity will slowly drop, right? Since gravity is an acceleration, that initial upward velocity is going to slowly dwindle to 0 as it rises. We've talked about how if you throw something upwards, velocity drops to 0 at the apex, correct? So, on its way up, that KE is going to decrease. And an interesting thing will happen. Oops. I'm going to demonstrate how I use the logic of conservation of energy to describe this part. So here we're going to examine the beginning energy levels of the bowling ball in comparison to its final energy levels, which is to say the energy levels at that highest point. So as it rises, total energy initial is going to be the sum of all of the initial forms of energy that it has. We've only talked about these two, so we'll add those two together on the left. Oops. So total of the initial energy levels is the sum of all of its initial energy types. And then on this side, this is looking at the energy level of the ball up here, at that apex, at that highest most point. And at that point, it's going to have a different amount of both types. So I'm going to write that in as KE final and GPE final. Different amounts of the same forms of energy. And so as the ball rises, initially, let's go one line down. Initially, it's got nothing but KE, right? But that changes on the way up. Because on the way up, its velocity is going to change and its height is going to change. It's going to elevate, so H will rise, and it slows down, so VF falls. And so over time, as this thing ascends, the current amount of KE will dwindle and the current amount of GPE will increase. And they increase, they change in tandem with one another. Because again, the energy can't be created or destroyed, it just has to change states. So if we examine like a midway point of this process, say the ball has slowed down enough to lose 50 joules of kinetic energy, that 50 joules has to turn into another type, GPE. Because again, it slows down, the KE drops as it rises, so the GPE increases, and it's a direct translation. Every single joule of KE that it loses, it will gain back as GPE. And you could plug in some halfway point here. You could look at, what are the totals part way up, where it would have some of both. But my question right now is, at what height is that transformation complete? What height is it going to rise to? What point will all that KE be gone and you've got as much GPE as you're going to make? What is the final velocity of the ball at that maximum point? Zero. So at that final height, this term is 0. So on the left, you've got all that initial KE. On the right, our final KE would be 0 at that maximum point. And we could then solve for what that maximum height is at that point. So height final would be 101.25 over 98, which, please correct me if I'm wrong, is just over 1 meter. So if you can chuck a bowling ball at 4.3 meters per second, you can get it a meter into the air. And then you should move because it will come straight back down. This process, this transformation of KE into GPE, happens for every projectile on the way up. Every projectile as it rises, you have this transformation. And the inverse transformation happens on the way down. On the way down, if we kind of reverse the perspective, up top you've got a lot of GPE but no KE, and GPE decreases as your height decreases, meanwhile your velocity is increasing, so your KE levels rise as your GPE levels fall, and you'll have all your KE back by the time you reach the bottom. You'll just be moving down instead of up. Notice that, again, energy isn't a vector, so KE doesn't actually care if you're moving up or down. The KE total remains, like the KE total doesn't care about whether V is positive or negative. Because within the formula, the velocity term is squared, So if it was ever negative, that goes away. Energy does not care what direction you are moving in or falling in. It just wants you to move. If you are energized, you just got to do something, right? Any questions about or concerns about this energy transformation process? Yes?
You can still use the original formulas just to find the height.
You can. In this case, that would work because if it's a projectile, you would know its acceleration. If your goal is just to find the height, I recommend Formula 4 as the most straightforward option. Assuming, again, at maximum height, final velocity 0, and you get the same answer. So yeah, if your goal is find final height, the old methods still work. But I want to kind of explore a familiar topic using the energy argument instead. As I've said a few times, there's often more than one correct way to get the final answer in here. How do you guys feel? Question?
And that's 1.03.
That's supposed to be an M for meters, sorry. Please call me out on my awful handwriting. I don't know if it's because I'm left-handed, a scientist, or both. Is that better?
Yeah, I just wanted to look.
All right. Now, I want to demonstrate at least one more method, kind of going in the opposite direction, and kind of showing a case where the old methods may not work perfectly, depending on what you happen to know or don't know. Because secretly, you don't even have to be falling for this method, for the energy method here to work right. As long as you are descending, you'll still lose GPE and likely be gaining some other form of energy instead. So it's true not only of falling straight down, it's even true of sliding. So instead of looking at this thing as it falls to the ground, instead we're going to look at a skier sliding down a slope. And the nice thing about skiing on snow is that friction tends to be negligible most of the time. So we're just not going to deal with that today. So here we have our poorly drawn skier on top of a 30-meter tall ski slope. Mass of 85 kilograms. And they're about to slide down this thing. 30 meters, that is a 10-story building, actually. So this is not a beginner slope. At least I don't think it is. I skied once, it didn't end well. So, in comparison to the ground, this person does have GPE at the top of that hill, even if they aren't strictly speaking going to be falling off of it. They still have GPE because they are elevated. So, even something sitting on a shelf has GPE, it's still elevated even if it doesn't actually fall off at full speed. As long as you could fall, as long as you have some height, some elevation, there is energy stored in gravitational potential for you. So in this case, we're actually going to start with a bunch of GPE, and I mean a bunch. About 25,000 joules worth. to get yourself. Again, consider GPE is not only the energy you have stored at that point, it's also the bare minimum amount of energy needed to get you up there from the ground. So if you walk up this hill, you're burning a lot of that yourself. Take the ski lift. And so that is the amount of energy that will be released once this person begins skiing. Questions so far? All right. For completeness sake, at the very start, before you actually kick off and begin screaming down the hill, how much KE do you have? 0. So, KE initial, 1/2 mV initial squared. So no KE to start with, it's all GPE before you start sliding. So, as this person descends, what's going to happen to their GPE level? It will drop. It drops as long as you're descending. You don't even have to be falling. And that's because this sunny side up egg is actually Earth and its gravitational field. So, gravity field, all objects with mass have one. And GPE doesn't actually care whether you are specifically falling, it just cares where you are inside of the gravitational field. And the further you are away from Earth's core, the more GPE you have. So technically, standing here on the ground, I actually have a lot of GPE if we consider height of 0 to be the center of the Earth, because I could fall all the way to the center of the Earth. I don't want to, but it's hypothetically possible. So again, this depends more on where you are in the field than whether or not you're literally falling. Same is actually true of magnets, as it happens, but that's something for next semester. So, this person's GPE will be released as they begin sliding down. I'm going to show the conservation of energy formula again, just to get you used to it. So initially, we've got a lot of GPE and no KE. And on the way down, GPE is going to drop as KE rises. And so we could look at, a halfway point. We could pause time right here and figure out how much GPE is left and how much KE you have generated at that point. But I find the more entertaining point in time to look at is right there at the bottom. We're going to figure out your max speed sliding down this thing from top to bottom. Initial KE we've determined to be 0. Initial GPE we've determined to be 24,990. Final KE is going to depend on the final velocity that this person is moving at. And final GPE is going to depend on what height we're examining. So if we choose to plug in a final height of 0, we will figure out the speed at that lowest most point. So again, we're looking for final speed at that lowest point. This is going to be the maximum speed, the point where all of that initial GPE will turn into final KE, and there's just no GPE left at all. At that point, final height is 0, this whole thing's just going to go away. That just leaves us with KE initial equals, GPE initial equals KE final. So V final will be the square root of 24990 over 1/2 of 85. Yeah, 85. And correct me if I'm wrong, I believe that makes the final velocity 24.25 meters per second. That is the fastest possible speed you could be going if you were this person sliding down this hill. For context, that is meters per second, and a meter is 3.3 feet. So this person is clearing 80 feet per single second. Black Diamond Hill. Questions? It's actually ruined the fun slightly. Snow is not perfectly frictionless, because nothing is. So this would be the top speed if friction didn't exist. Realistically, you would be going slower, which is good, because most people would probably hurt themselves going that fast. I know I did, past tense. So again, this is if there wasn't friction, but I will tell you when we will count friction versus when we won't. Frictionless, book it. In a world with friction, we'd add an extra term here to account for the amount of energy that friction takes away, the work not conserved by friction. We'll practice that at a later date. Questions for right now? All right. So, we've looked at two forms of energy. We've looked at how they can transform into each other, and reminded ourselves about the law of conservation of energy. We are going to end today by introducing a third type of energy to make life a little more complicated, because lab this week is going to involve this third type of energy. It's a new form of potential energy. It's another place that energy can be stored, and that's in springs. Springs, the object, not the building. Elastic potential energy is a form of potential energy that is stored within a stretched elastic object. You've probably noticed at some point in your life that if you take a spring or a rubber band or something defined as elastic, the physics definition for elastic is an object that is able to deform and then return to its original shape of its own volition. This spring is a good example, because if I deform it, which is to say change its shape, it goes back all by itself. Non-elastic objects don't fix themselves, which is, say, what happens if you hit a rock with a hammer. The rock breaks and then stays broken. Whereas this, ow, returns to normal. And when you stretch an elastic object, you do work on it. So when I do this, I exert a force over a distance. So I'm doing work. That means I'm using up energy in this act. And that energy is currently being stored inside of the spring. And that energy is then released when you physically release the spring and, say, launch well, at least in the case of me growing up, when I would stretch a rubber band and then release the rubber band, the energy stored inside of that elastic object is released, and the rubber band launches itself at my little brother. And then Dad would launch several at both of us. Any elastic object, springs, rubber bands, hyper bouncy balls, any sports equipment that's meant to bounce, anything that is elastic and can deform and return to normal, energy is stored temporarily in that deformation and then released when it returns to its original shape. Again, this form of energy is called elastic potential energy. This is the new formula for it. EPE equals 1/2 times a new concept K, I'll get to that in a second, times x squared. And the x in this formula is the magnitude of deformation. Physically, how much something is stretched. So if this is the object I'm stretching and I make it, if I exert enough force to make it 1 meter longer than it was already, x would be 1 meter in that equation. That would be the energy needed to make this thing 1 meter longer, and the energy that is released when it returns from 1 meter longer to normal. So, slingshot, you deform the spring, make it longer, energy is stored in the spring, and then whatever you have loaded into the slingshot, the energy that was stored in the spring becomes kinetic energy in your projectile. Does that sound all right so far? All right. Again, this happens for anything that is elastic, and that includes like basketballs and things like that. Maybe hard to notice without freeze frame camera, but the second this thing hits the floor, it does squash. And that means that it is deformed. And then it goes back to normal, right? The change in its size would be the x in this formula. And that means that while it's squashed, there's energy physically stored inside of the ball. And then once it springs back to normal and kicks off the ground, that energy is re-released into the kinetic state, and that's why it then is able to rise back up off the floor. And that's why things that aren't elastic, like most objects, don't really bounce. They don't store the energy from the impact, and they don't release it later. They just lose it. And this is what lab is going to partially involve. Lab this week is actually going to involve all 3 types of energy we've looked at so far. The last thing I'll say about this is the K in this formula is called spring constant. It's a measurement of how elastic the object in question is. An object with a higher spring constant takes more force to deform and it stores more energy. A really stiff spring would have a very high K value, whereas this is very easy. That's a very low K value. Questions thus far? Or questions about anything as lecture ends? All right, let me know if you need anything. Bring all these notes to lab this week whenever you have it, and have a great day.